Rapamycin and other mTOR inhibitors are among the most promising pharmacological tools currently being explored to extend health span and slow the biological processes of aging. Though these agents do not directly lengthen telomeres or activate telomerase, their ability to modulate the mTOR, mechanistic target of rapamycin, pathway places them at the center of interventions that help preserve cellular function and delay age-associated decline. The connection to telomeres lies in their systemic effects on senescence, autophagy, and metabolic regulation, processes that, when optimized, may reduce the rate of telomere attrition and help cells maintain genomic stability over time. Rapamycin, originally discovered as an antifungal agent and later developed as an immunosuppressant, functions by inhibiting the mTORC1 complex, a central nutrient-sensing regulator of growth, metabolism, and protein synthesis. In conditions of nutrient abundance, mTORC1 promotes cellular growth and proliferation. However, persistent activation over time contributes to cellular aging, chronic inflammation, and accumulation of damaged proteins and organelles. By dampening mTORC1 signaling, rapamycin effectively mimics a state of caloric restriction or nutrient scarcity, which has been associated with increased lifespan across multiple species, from yeast and worms to mice, and potentially primates. In this context, mTOR inhibition exerts several protective effects that indirectly benefit telomere health. One of the most well-documented mechanisms is enhanced autophagy, the cellular process by which damaged proteins and organelles are degraded and recycled. Efficient autophagy reduces oxidative stress and improves mitochondrial function, both of which are crucial in slowing telomere erosion. Reactive oxygen species generated by dysfunctional mitochondria are one of the primary drivers of DNA damage at telomere ends. By preventing the accumulation of damaged mitochondria and other stressors, rapamycin reduces the environmental burden on the genome, allowing telomeres to shorten at a slower and more controlled rate. Another critical benefit of mTOR inhibition is its impact on cellular senescence. As cells divide and telomeres become critically short, they often enter a state of irreversible growth arrest, known as senescence. These senescent cells not only cease dividing but also secrete a variety of inflammatory molecules, a phenomenon known as the senescence-associated secretory phenotype, SESP. The SESP can promote local inflammation, tissue dysfunction, and even propagate senescence in neighboring cells. Rapamycin has been shown to suppress the SESP and may delay the onset of senescence in otherwise healthy cells. This helps maintain a more youthful cellular environment where telomere erosion does not automatically lead to dysfunctional or inflammatory cell states. Interestingly, some studies have reported that rapamycin-treated cells exhibit a delayed shortening of telomeres, likely due to improved metabolic and redox balance rather than direct telomeric effects. Moreover, rapamycin's systemic benefits include improved glucose metabolism, reduced inflammation, enhanced stem cell function, and extended lifespan in mice, even when treatment is initiated in midlife. These findings suggest that mTOR inhibition may extend the time before telomeres become critically short by preserving overall cell and tissue health. The safety of long-term mTOR inhibition is an ongoing area of research. In clinical contexts, rapamycin has been safely used in transplant recipients and patients with certain rare disorders. However, its immunosuppressive properties and potential side effects, such as impaired wound healing, glucose intolerance, and lipid abnormalities, have raised concerns about widespread, continuous use in healthy individuals. That said, more nuanced dosing approaches, such as intermittent low-dose regimens, are now being explored and appear to retain many of the anti-aging benefits without the adverse effects seen with chronic high-dose therapy. From a broader perspective, rapamycin and mTOR inhibitors represent a shift in longevity science. Rather than targeting a single biomarker like telomere length, these interventions address the underlying systems that determine cellular resilience. Telomeres do not erode in isolation. They shorten faster when the cell is inflamed, oxidatively stressed, or metabolically imbalanced. By creating a cellular environment that is less prone to damage and dysfunction, rapamycin helps preserve the conditions under which telomeres degrade more slowly and cells remain functional longer. In sum, while rapamycin does not directly extend telomeres, Its influence on autophagy, inflammation, and senescence makes it a powerful candidate for protecting cellular integrity. It underscores the idea that telomere health is not just about adding nucleotides to chromosome ends, it's about slowing the processes that wear them down. As research into mTOR modulation continues, rapamycin and related compounds may become essential tools in our expanding toolkit for healthy aging, offering not only life extension but better quality of life through the preservation of core cellular systems.